Okay, so here is the first of many videos about graph theory. um, so before you watch this video, or before you watch any more of it, please read Chapter 1 up to Section 1.3, including Section 1.3. I'm really not going to go over all of this in the video. The video is not a replacement for reading this. And also, you really should read this before you watch the rest of the video, or you won't necessarily understand the things that I'm saying. I'm going to go over some of the things that are in here, but like I said, you should read this first. And yeah, so of course this is the textbook, which is by Chartrand, Lesniak, and Zhang. So right, let's first talk about Theorem 1.4 in the book, which they call the first theorem of graph theory. This is often also called the handshaking lemma. So here it is. If G is a graph with size m, of course the size of a graph is the number of edges in the graph, so it has m edges, then what this says is if you add up all the degrees of all the vertices in the graph, so you take for each vertex v, you add up the degree of v. You do that for all the vertices, that the sum that you get is going to be 2m, 2 times the number of edges. And there's a formal proof in the book, but I find the proof a bit terse, especially maybe for, at this level. The proof, I basically summarized down here. The proof is supposed to be that both sides of this equation, count every edge twice. And that's kind of obvious for the right side. That's just the number of edges times 2. And so the explanation for the left is supposed to be that every edge gets counted twice. But let me break this down in terms of an example, actually. So here I have a graph. I just drew a particular graph. And it's got 5 vertices and several edges, I guess 6 edges if I count them. 1, 2, 3, 4, 5, 6. And let's just verify that this is true, that if I add up all the degrees, I get 2 times the number of edges. So here I added up all the degrees. So this one has degree 2 because this vertex is touching 2 edges. So that's the 2. This vertex has degree 3, 1, 2, 3 edges, so that's the 3. I think I did this vertex next, so this one has degree 2, that's the 2. And then I did this vertex, this has degree 3, that's the 3. And then this has degree 2. I add all those up and I get 12. So I just did the left side and I got 12. Meanwhile, if I do the right side, we already said we have 6 edges, 1, 2, 3, 4, 5, 6. So I'll just do 2 times 6, and sure enough, I get 12. And of course, this example isn't supposed to be a proof, but I would like to use this example to illustrate the proof, because I can break this down better in a way that you may be more understandable. When I do this degree sum, once again, what I'm doing is this 2 is corresponding to this vertex, and what I'm doing for each vertex when I find its degree is I'm counting the number of edges that it touches. So instead of just counting them, why don't I name them? So this 2 was because I had this edge, and they have names. So this 2, I can sort of break down into these are the 2 things that I counted to get that 2. These are the 2 edges. This 3 was the degree of v, and then that was this edge, and this edge. So let me actually name them. UV, Vx, Vw. This 2 was the degree of x, and that was these 2 edges. That was Vx and xw. So that was this 2. This 3 was the degree of this, so that's this one, and this one. Vw, xw, wy. So that was the 3, and then finally this 2 was the degree of this, so that was this edge and this edge. That was wy and uy. And of course, if I count all of these things, there's a total of 12 of them again. Of course there are. But the point is, and this is how I'm illustrating the proof, in this list, this is just a list of edges. In this list, every edge appears exactly twice. For example, UV appears here and here. What's another edge? Say XW. That's here and here. I don't know. I'm not going to do this forever. So what about VW? That's here and here. Yeah, so then I'm almost done, actually. Here's VX and VX. UY and UY. And WY and WY. Every single edge appeared twice, and that makes sense because, you know, when I'm listing all of these edges, say, let me pick on an edge like UY, that got listed when I was doing the degree of U, which was in this column. I did the degree of U in this column, so I listed all of the edges that touch U in this column. And then somewhere else, I listed all of the edges that touch Y. That would be at the very end. I did all the edges that touch Y. So then this edge appeared here and here. And that's going to happen for every single edge. Every single edge has exactly 2 endpoints, and it's going to appear in the column for one endpoint and in the column for the other endpoint, so it appears on the list twice. So there you have it. That's my breaking down of the proof. The truth is, this is a fairly standard proof for people who are more familiar with counting arguments. That this is a counting argument. But I thought I might as well break it down further for you, just so everybody's on the same page. Anyway, let's talk about isomorphism. So I went ahead and put the definition of isomorphism here. This is also in the book, but here it is. So two graphs are isomorphic if there's a bijection from the vertex set of the first graph G to the vertex set of the second graph H, such that for all two vertices U and V in the graph G, U and V are adjacent in G if and only if phi of U and phi of V are adjacent in H. For example, these two graphs are isomorphic. And maybe I should explain just more intuitively. Graphs are isomorphic if they're, roughly speaking, it's just two different ways of drawing the same shape. I'm allowed to take this drawing of the graph and maybe move this vertex over here somewhere, as long as I take the edges with it, as long as it's still adjacent to the same other vertices. I can move it around. I can give vertices different names, and doing things like that results in isomorphic graphs. Isomorphic, in a way, it means essentially the same. In a more technical way, it means exactly this, but in an intuitive way, it means that they're essentially the same. So let's look at this more technically, because if I'm saying that these two are isomorphic, I should be able to give you an isomorphism. And by the way, the isomorphism is just the name of this function phi. So what do I want to do? Roughly speaking, I can sort of see the correspondence between these two graphs. And these are relatively simple graphs. This is just what we call a 5 cycle. It's just it has 5 vertices, and for the edges, it just kind of goes around in a circle. Or not really a circle, but it goes around in a closed loop. And there's a way of viewing this star as a closed loop, right? In elementary school, we always drew, we all know how to draw that. Go here, 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 here. And roughly speaking, what I'm doing here is I'm telling you the correspondence. On this one, I go around like this. On this one, I go around like this. So here we go. Let's do an isomorphism. And actually, the truth is there are many isomorphisms from this graph to this graph, and we just have to find one isomorphism. And that can help. Realizing that can help us. So the truth is, on a cycle like this, it doesn't really matter where you start. Why don't I guess I'll sort of go in alphabetical order. Yeah, down here, they're in alphabetical order anyway. So phi of u, phi of v. So why don't I say phi of u is 1? Because it shouldn't matter which vertex over here I start with. Again, isomorphism isn't something where it matters if I do something like move vertices of the graph around. Like I could take this graph and just spin it like this. So like 1 would be here, 5 would be here, 4 would be here, 3 would be here. But the picture would look basically the same. It would still look like this star-looking thing. So it doesn't really matter which one of these vertices I start with. So I very much arbitrarily said that phi of u would be 1. And now I'm going to do what I said about like going around. So on this graph, I'm going to go around like this. On this graph, I'm going to go around like this. So my next vertex is V, and here, well, my next vertex, well, I could go from 1. I could go around this way, or I could go around that way. So I would say phi of V looks like it could either be 3 or it could be 4. Again, there are many isomorphisms, so let's just pick something and hope for the best. Now that I've done this, what's the next vertex? So here I'm going around like this, U, V, and then the next one's W. Here I went from 1 to 3, and then the next one should be 5. So W corresponds to 5. And I'll start going faster. The next vertex is X. That should be 2. And then the last vertex is Y, and this is going to be easy because there's only one thing that isn't on the list, and this has to be a bijection. This would have to be 4. So this is an isomorphism, and we can really check it. I don't want to fully check every single thing here, but what is the property supposed to be? The property is supposed to be that if 2 vertices are adjacent in G, then if I look at the images under the isomorphism, that those 2 vertices are adjacent in H. For example, let me take 2 vertices here that are adjacent, like say X and Y. That's an edge of G. Now, if I look at their images under the isomorphism, they should be adjacent in H. The image of X is 2. So I'm doing phi of X, phi of Y, and phi of X is 2, and phi of Y is 4. And sure enough, if I look at the graph H, 2 and 4 are indeed adjacent. And why don't we check another thing, because really this is supposed to be if and only if. So two vertices are adjacent in G if and only if their images are adjacent in H. We just checked two vertices that were adjacent in G. Why don't we check two vertices that are not adjacent in G, like say U and W. UW is not an edge of G. So if I do phi of U, phi of W, that should not be adjacent in H. So phi of U is 1, phi of W is 5, and sure enough, 1 and 5 are not adjacent in H. So I didn't check every edge, and I didn't check everything that isn't an edge, but I checked one edge and I checked one non-edge. But this is an isomorphism. It's easier, you know. It's easier to check this with your eyes, frankly. It's very easy with your eyes. You just check for every edge here. I've got U and V. U and V are here. Their images are here. That's 1 and 3. And then you look here and you can check that 1 and 3 is an edge. You don't really need to write all of this down. The easiest way to check this is with your eyes. Okay, so here is a description of theorem 1.6 in the book, that if two graphs are isomorphic, then they have the same order. Recall, this is the number of vertices in a graph. They also have the same size, which is the number of edges in the graph. And they also have the same degree sequence, which let me leave that for just a minute from now. But so in our example above, we had two graphs that were isomorphic, and let's check these things. They both have order 5 vertices here and here. They both have size 5. So that's the number of edges. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let me tell you what degree sequence is. We're going to talk more about degree sequence in probably next week, but I'll just tell you out loud what it is now. The degree sequence is I list the degrees of all the vertices. And what I do is I put them in non-increasing order. So I start with the largest one, and then second largest, and then third largest, and then fourth largest. Of course, there might be a tie. You might have several vertices that have the same degree, but then you just list them. You list that number several times. So actually, in this graph, every single vertex has degree 2. So if I start with the largest one, I'm going to write a 2, and then, well, the second largest is also a 2. Actually, the degree sequence of this graph is just 2, 2, 2, 2, 2. And it's the same for this graph. Every vertex has degree 2. And of course, again, this example isn't a proof. There's a proof of theorem 1.6 in the book that I encourage you to read. Okay. So let me do a couple of examples that just say R, G, and H isomorphic. If they're not, then we should explain why they can't be, that there can't be any isomorphism. And if the answer is yes, if we're saying they are isomorphic, then we have to give an explicit isomorphism. And by the way, an explicit isomorphism is like what we just did in this example. When I say an explicit isomorphism, I want to know what's phi of this, I want to know what's phi of this, I want to know what's phi of everything. That's an explicit isomorphism. So we're starting this pretty easy here. These two graphs are not isomorphic because they don't have the same order, right? We just said in theorem 1.6, two isomorphic graphs always have the same order. This one has order 3, this one has order 4. That is an explanation. The answer was no, and we provided an explanation. Let's take a look at B. So here I've got two graphs, and when you do this type of problem, it's best to start checking the easy things first. And the easiest thing to check is it's the test that we picked on last time. It's just checking whether they have the same order, the same number of vertices. So this one has 4. This one also has 4. So what does that mean? Last time we found different orders and we said now the answer is no. This time we found they have the same order. That doesn't mean anything, unfortunately. That doesn't mean the answer is yes. That means that we don't know yet. We don't know whether they're isomorphic. What I would recommend is start thinking about the next thing, which is, well, they're kind of in order here. Check whether they have the same size. Check whether they have the same number of edges. This one has size 3. This one has size 1, 2, 3, 4. Looks like we're done. The answer is no. G has size 3. H has size 4. So that's an explanation. All right, let's do C. So the first thing to check is, do they have the same number of vertices? I've got 5 here and 5 here. All right, that means we still don't know the answer. The second test is to check whether they have the same number of edges. I go 1. Yeah, maybe it'll be easier if I go around 1, 2, 3, 4, 5, and then this one makes 6. And well, here I see 1, 2, 3, 4, 5, 6. So they have, maybe I'll start summarizing what we have. First, we checked the order. We said it was 5 vertices and 5 vertices. Then we checked the size. Then we said it was 6 edges and 6 edges. Well, the next thing to check would be the degree sequence. G looks like it has, actually, let's do this. The degree sequence of G. We start with the largest degree first. I see a degree 3 and another degree 3, but I don't see anything with degree larger than 3. So my degree sequence is going to start 3 and then another 3, because that's this one and this one. And then other than that, I've got a degree 2, degree 2, degree 2. So 2, 2, 2. All right. If they are isomorphic, then H will have the same degree sequence. So what's the degree sequence of H? So I look around to find the largest degree vertex, and I see a degree 4 vertex. So already we know that the answer is no. These can't possibly be isomorphic because already I see that the degree sequence is not the same. This one started with a 4. Just for fun, let's go ahead and write the rest of the degree sequence. I think they're, yeah, all the other vertices are degree 2. 2, 2, 2, 2. So 2, 2, 2, 2. But they, you know, they weren't the same. So no, they're not isomorphic because they have different degree sequences. Okay, I'm going to do more examples where we tell whether graphs are isomorphic to each other, but I'm going to cut this off and make it a new video.